So today we're going to factor using special products, and I apologize because my voice is going out on me. And if you recall from Chapter 6, we had 3 different factor patterns for special products. The first one that we're going to look at is for a perfect square trinomial. So the factor pattern would be a squared plus 2ab plus b squared. That's a perfect square trinomial, and it would factor as a plus b squared, or a squared minus 2ab plus b squared, and that would factor as a minus b squared. So as you're looking at your trinomial, if you look over at these patterns, by the way, the a and the b have nothing to do with standard form, which is ax squared plus bx plus c. This just has to do with factoring. The a represents the first term in the binomial, and the b represents the second term. So they took the first term, squared it to get the a squared. To get the middle term, they took a times b, and then doubled it, multiplied it by 2, and that's how they got the 2ab. And they took the second term, this b, squared it, and they got b squared. So that's the shortcut to multiplying a plus b times a plus b, because that's what a plus b squared is. So there are 3 tests that you need to apply to determine if the trinomial that you're looking at is a perfect square trinomial. So as you look at these patterns, you notice that both of them have a positive a squared and a positive b squared. So I like to call these my bookends. So your bookends are not only positive, but they're perfect squares. And then, so those are your first 2 tests, positive bookends, and then they're perfect squares. And then the final test is to see, does the square root of your bookends, which the square root of a squared is a, and the square root of b squared is b, so does a times b, the square root of those bookends, times 2 match your middle term here. So as you look at this trinomial, this x squared is a perfect square. This 36 is a perfect square because their square roots, so the square root of x squared is x, and the square root of 36 is 6, because 6 times 6 is 36, x times x is x squared. So that's our a, x represents our a, and 6 represents our b. So I have positive bookends and I have perfect square bookends. That does not mean it's a perfect square trinomial. We have to test it. So we're going to test it using the 2ab. So I've got 2ab equals 2 times, and I'm going to multiply by my a, which we found to be x, and my b, which we found to be 6. This happens to give me 2 times 6 is 12, times the x gives us 12x. That 12x does indeed match the middle term. So because it passes all 3 tests, it is indeed a perfect square trinomial, and immediately I know that the factor pattern is one set of parentheses squared. Then each one of these terms gives something to the factoring here. The first term gives us our a, because remember we've got a plus b. So we already figured out what a was and what b was. So a is going to go here and b is going to go here. So I have my x's here. Whoops, I want to change colors. X is here and 6 is here. Then to determine your middle sign, the middle term determines your middle sign. So since the middle term is positive, the middle sign is positive. And so then this is your answer. Now some of you could be saying, I don't want to go through that. I'm just going to use my t-chart. So if you go and use your t-chart, it takes you a lot more time to use that t-chart. For instance, remember in your t-chart we have to take the coefficients of the bookends. So the coefficient here is 1 and multiply it to this other bookend, 36. So 1 times 36 is a positive 36. So you'll set up your t-chart with a positive 36 because that's A times C. Sorry, that was the end of the period. And then B equals 12, that's your middle term. And then we're going to add and subtract those. So the factors of 36 would be 1 and 36. They add to give you 37 and subtract to give you 35, neither of which are our middle number, which is 12. The next number after 1 is 2. 2 goes into 36 18 times. You add them, you get 20. You subtract, you get 16. Not our middle term. Next number after 2 is 3. 3 divides into 36 12 times. You add them, you get 15. You subtract them, you get 9. Again, not our middle term. Next number after 3 is 4. 4 divides into 36 9 times. You add them, you get 13. You subtract them, you get 5. Still not our middle term. So this long way is taking a long time. Next number after 4 is 5. 5 does not divide into 36 because 36 does not end in 0 or 5. Next number is 6. 6 divides into 36 because 2 and 3 do, and it goes in there 6 times. Add that, you get 12, and there it is. So we're going to use these terms in 12. The sign of 12 is plus. So the bigger the two terms, which they're the same, gets you a positive. So the only way to get a positive product with a positive 6 is for the other 6 to also be positive. And so we are going to, since, remember there's a shortcut, if there's no coefficient in front of the squared term other than 1, we don't have to actually rewrite the 12x and replace it with 6x and 6x. You could, but it's more work. So instead we can just take a little bitty shortcut and we can throw that into parentheses. Our variable is x, and they're going to put each of the plus 6's here and here. So this would be our answer. And so as you can see, x plus 6 times x plus 6 is identical to x plus 6 squared. So I would much rather do it this way because this is a lot more work, although both of them will give you the same answer. So let's look at example 2. For example 2, if we're going to determine if it's a perfect square trinomial, look at your bookends. First test is, are they positive? Yes. Second test is, are they perfect squares? This one and this one. Well, let's test it and see. The square root of 4x squared, the square root of 4 is 2. The square root of x squared is x. Square root of 9 is 3. So they are perfect square bookends. But that's not enough. If this is a perfect square trinomial, it will be following the factor pattern of a squared. Because the middle term is negative, we would be choosing the minus 2ab plus b squared equals a minus b squared. So in order for this to be a perfect square trinomial, we need to test it to see if the 2x and the 3 are going to make that middle term that matches the pattern of 2ab. So let's test it. 2 times a times b equals 2 times, and then if you recall, this is our a, so I'm going to put in 2x, squeeze it in there for our a, and this is our b, so I'm going to put in the 3 for our b, and then I have to multiply all three of these together. 2 times 2 is 4, 4 times 3 is 12, times the x is going to give us 12x. And then you're going to ask yourself, does this match the middle term? It does. Don't worry about signs. We'll deal with the signs in a minute, but yes, it matches. So ignore that. That was Mrs. Kennedy laughing at me. Anyway, so this does match. It matches. And we'll deal with the signs, but since it passes all three tests immediately, you should be realizing that its factor pattern is one set of parentheses squared. And so each one of these terms contributes something into the factoring here. So if you recall, it's a minus b for this particular one because our middle term is negative. So this represents our a because the square root of a squared is a, and that's what we came up with here. Same thing, the square root of b squared is here, 3. So our a is going to be 2x. Our b is going to be the 3. And then our middle sign is the negative because it came from our middle term. So the 4x squared gives us the 2x, middle term gives us the sign, and the 9 gave us the 3. And so this is our final factoring for a perfect square trinomial. If it doesn't match, it's not a perfect square trinomial. Let's look at example 3. So for example 3, start out with your test. You've got a trinomial. Your bookends are positive, and the next test is, are they perfect squares? So let's find the square root. The square root of 9 is 3. The square root of x squared is x. So that's a perfect square. Then the square root of 4, as we did previously, is 2. So our bookends are positive, and they're perfect squares. But that's not enough. We have to use the final test, which is 2 times a times b. Again, we're trying to see, does it match a squared minus 2ab plus b squared? And then if it does, it would factor as a minus b squared. Again, I chose this particular pattern here with a negative 2ab because my middle term here is negative. So I'm not putting a negative here because I would make the signs match anyway. So we've got equals 2 times, and then you're going to put in your a, which is the 3x, and your b, which is the 2. And if you multiply together, 2 times 3, you get 6. 6 times 2 is 12, times the x gives you a final answer of 12x. And then, does it match? No, it does not match. And so your reasoning why is going to be it's not a perfect square trinomial. Because it does not pass the 2AB test. So if it doesn't pass any one of those 3 tests, bookends are positive. If they're negative, then it's not going to be a perfect square trinomial. Bookends are perfect squares. If they're not, it can't be a perfect square trinomial, and that final test is the 2AB. Now you will notice that if you had ignored this 2, and let's just kind of cover it up here, if you ignore the 2, the 3 times the 2, or the 3x times the 2 is a 6x. You would have been sucked into thinking that it matches. And we can't force this to match by dividing it by 2. That's not the point. You have to do 2 times a times b, and whatever you get, if it does not match exactly, it's not a perfect square trinomial. This does not mean it's not factorable, this whole trinomial. It just means it's not a perfect square trinomial. So if you were to factor this, which I'm not making you today, you would have to then revert to the t-chart with grouping. So you'd have to do a times c, find your b, find all your factors of that product, and so forth. But I'm not going to make you do that today. All right, so let's look at some binomials. So example 4. Now in example 4, we have a binomial, 2 terms, and we have a minus. So our other special products would be the difference of 2 squares. Squeeze that in there. And its factor pattern would be a squared minus b squared is equal to a plus b, a minus b. So if we have two perfect squares, which these are, and we have a difference, then the shortcut or the pattern always is to take the square root of a squared, which is a, and the square root of b squared, which is b, and you put them in two parentheses. One parenthesis has a plus and one has a minus, so you'll end up with a plus b and a minus b 100% of the time. I mean, you could still try to use the t-chart because you're missing your middle term, right? But your inner and outer terms will always cancel. So that's why the pattern works. So these are my favorite to factor because they're easy. Now, we do have our difference. This is a perfect square. Why? Because the exponent here on the variable is even. So 2, 4, 6, 8, any even number means it's a perfect square. So you're not always going to see an x squared, a b squared, a p squared, a d squared. Then you were to memorize your perfect squares. 81 is a perfect square. So as soon as I determine, and I'm going to find their values here. So the square root of x squared is x, and the square root of 81 is 9. So as soon as I realize that, oh, I have the difference of two perfect squares, I know I'm going to have two sets of parentheses, one with a plus and one with a minus. And then these values, this is going to go in the first slot, the x, and the 9 is going to go in the second slot because this is our a and this is our b. So I'm going to place x here and 9 here, x here and 9 here. And if you went and remultiplied, use the double distribution method or the box method, you would see that it does, this is my answer, but I'm just going to check it and prove to you right here, this is our answer. I'm going to prove to you that if we distributed, so distribute the x, so x times x is x squared, x times negative 9 is negative 9x. Then distribute the 9. 9 times x is a positive 9x. It's a like term to the negative 9x. And 9 times negative 9 doesn't have a like term, so it gets its own column, negative 81. As you can see, the two middle terms, the 9x's, cancel because they're opposite signs. And you end up with an x squared and a minus 81. Which is identical to what we started with. So that's why this is the correct answer. And if you have the difference of two perfect squares, it will always work out that way. So let's look at example 5. Again, you're going to determine, do I have the difference? Yes, the difference means subtraction. And is this a perfect square and is this a perfect square? So let's see if we've got perfect squares. All right, so the square root of 9p to the 4th. So the square root of 9 is 3. Remember, your index here is 2, and you're going to divide this exponent by that index. So to get the square root of p to the 4th, you divide that by 2, so you get p squared. And then the square root of 16q squared, square root of 16 is 4, square root of q squared is q. So it is the difference of two perfect squares, and so I know for a fact the pattern is going to be two parentheses, one with a plus and one with a minus. The 3p squared goes first, and then the 4q. 3p squared and 4q. And there's your answer. Last problem. So for example 6, again, we want to determine, is this a difference of two squares? So we have a difference, so we're good. And then we need to look to see, are these two perfect squares? So right now, the square root of x to the 6, is that a perfect square? Well, remember, if we took the square root of it, the index is 2, and so we would divide that by 2, and we get x cubed. So yes, x to the 6 is a perfect square. Then look at your second one. Is 7 a perfect square? Is there any number times itself that gives you 7? No. So 7 becomes our problem right here. This is not a perfect square. So no, it is not the difference of two squares, and it cannot be factored in a plus-minus pattern. It doesn't necessarily mean it's not factorable, but it can't be factored as the difference of two squares. So the only other way that you can factor a binomial is to take out a greatest common factor, and as you look at them, coefficient of -7, coefficient here is 1, they don't have a number in common, and they don't have a variable in common. So this is not factorable, it's prime. And that's it, you're done. So your homework, your classwork for today is page 494, 1 through 3 all, and 8 through 10. Have a fabulous day.